explorers, and welcome to another video. Today we're going to talk about more 3D printing. It's gonna have some coding involved, but it's mostly somewhat successes in my case and some total failures. But I learned a lot along the way. So I'm gonna share a lot of the learnings that I did along the way. So when it comes to 3D printing, you use some kind of program to create something that you want to be printed, and there is a lot of different models out there that you can already use. And one of the models was for creating this part that you could put in your rack. So you actually got some kind of a shelf, and it was modular, so you can actually snap them together, and then you have 3 different compartments. I'm showing a video about it now, and in those 3 compartments you could put some kind of different modules. And the modules are similar to this one, where you have this kind of inserts here where you put the model down into it. And these inserts were in the way for my server, so I actually removed them. And I printed one of these just to get a kind of estimate on how large it is and if my server would fit. And it did. So I could actually use the whole compartment and put my servers in there. But you also see that it's pretty shallow. So I wanted to lengthen it a bit so I could have both the server and the power plug as well at the bottom here. So the transformer that actually transform into, I think it's 5 volts or something like that, into the server. So I did that as well. I lengthened it and I put some kind of a wall that should put that power converter solid in there. It wasn't good because it fell out all the way all the time, so I had to actually use tape to actually get it to stick in there. But I got it to work somewhat, so it's now installed in my rack. So I have 3 different compartments where my three of my servers are. So that was a somewhat success. Another thing I wanted to do was to take one of my servers, take away the bottom part of the server, and then create a new bottom plate, and then create this kind of a compartment where I could put one of the larger hard drives. So this is a hard drive holder that I printed. So this was what I wanted to use at as a bottom plate. And it also has this kind of ledge or a snapping part here. Not really that great. This was very fragile, so it actually broke on me separate times. And this was the first one I printed, and then printed another one where I put an extra hook on it. This kind of an arrangement that snapped off because it wasn't big enough, so it didn't hold. And I also printed this part that I put into the server. So this is the first print. Sadly, the holes were too small here, so I had to widen them in order to get the screw in. The next one that I actually tried out had this larger hole and also had this kind of insert here that I could snap on, but this kind of a thing that I put in, it was too small and fragile, so it actually broke off. So that was not a good solution. Then I switched program, so I actually could use coding in order to create something, and I also switched color. So in this case I created a wider kind of insert, but then again the holes were too small, but with programming you can change that up. So the final product is this kind of thing, where you have a hard drive down there, and I also have this kind of mechanism that it's staying there, and then I can take it off. But it's actually having the hard drive in here, so I actually have it connected. So what was the big problem here? For all that you out there that actually knows, pause the video and type a comment so I can laugh about myself later on. So the problem is that this is totally stupid. It's over-engineered and it's also totally wrong because it will never work. As I said before, this up here is using 5 volts or similar. So we convert things, put it into this and running 5 volts and some ampere. And then you put it into this hard drive down here on the 5 volts rail, and the hard drive will not be detected. And I looked into the specification of a 2.5 inches hard drive and a 3.5 inches hard drive, and the difference is the power connector. So the power connector for 2.5, it will populate the 5 volt rail and give power to the hard drive. So that's why the 2.5 hard drive works, and it always will work in any system because you always have this 5 volt connection. But when it comes to these larger drives, they need more power. So you also have a 12 volt rail going into the system. So you have one more power connector. So you have both 5 volt and 12 volts going to these larger drives. And that will never be supplied by this computer. So I never got a 12 volt and never got power enough to run the hard drive. Of course, I could buy some kind of extra cable and transformer and so on, but this doesn't really make the purpose of this build feasible. It's not really what I was looking for. So sadly, this was a total failure because I didn't read up on the specifications that you actually need to give more power to larger drives. Who knew? But let's switch over to my computer here and we can see the first program I was using into 3D model. This is Onshape, and here we have one of the parts. We have the other part here where I looked into these kind of small clamps. I also have this bottom plate that I imported, and I also did some changes to it. I'm not sure that I have this in this file here. The problem with this program is that you need to sketch something and then you extrude that sketch, and then you sketch something and then you extrude that sketch, and then you sketch something. Yeah, you get the point. You actually have to draw something, then extrude that drawing either as a part or an empty room. So you actually need to draw all the different crevices and so on. And if you need to change the dimensions and so on, you need to change the drawing. The good part with the sketch, if we look at this one, is that you can put in this kind of length measurements. So you can actually create dividers on how large things should be, but it's not really that intuitive for me. Then you extract this as an STL file. Then I will put it into a program called Orca Slicer, and I will slice it up on my plate here. I will export a G file, and that is a code language that tells the 3D printer how to print everything. And when you have that G code file, in my case, I will send that up to Creative Cloud, and it will print it out on my 3D printer. So I'm just waiting for the day when this Creative Cloud is hacked and every 3D printer out there will print something phallic or something like that. That will happen to my printer as well. Anything online will be hacked. I could actually put the G file on a USB stick and put it to my printer if I want to, but it's already connected to the cloud, and this is a little bit more convenient. But I don't really like that they have a cloud solution for this. I much more would like if I had a program on my computer and then send a file over the local network. That would be more reasonable to me. So that was about what I did at the beginning, but I did have to make so many changes to the measurements. So making this was super annoying. So then I was visiting a friend, And he was making this outside gym where he was creating models in order to build something in his yard. And he was using a totally different program that you actually used programming in order to create your models. So I thought that I would look into that and use that, and with some help with the GPT and getting me started, and then I could continue creating things when I understand the language more. I actually created the models in something called OpenSCAD. So OpenSCAD is this kind of modeling tool where you write code in order to describe how things should look. So if we first look at this bottom plate with pipes, so this is my first model that I did. So here you can look at the model, not change anything or draw anything, just look at it in different directions and so on. And then you type code over here. So you have variables, plate length, plate width, plate thickness, and then you have post, outer diameter, inner diameter, screw hole diameter, post height, thread base thickness, and then we have the slit over here with the width and the length and a position from edge. And then you have the post positions. So these are the 4 different posts and where they are placed on the plate. And then you print the base plate. And here we have something called a difference. And the difference takes the first argument in the difference as the actual 3D part. And then every other thing that you put in is extruded or extracted from that part. So first we create this cube, which has the plate length, plate width, and plate thickness. So it will create a full plate here. And then we do changes to it. So if I change this code here, remove these, you see that everything that was inside of the plate is removed. Even the holes are removed. And then if I put these back here, you see that I get the holes back. So if we do like that, we can see that we get the holes back in the plate. And I also needed to have a little bit of a diffing factor, because if you go do it exactly the size of everything, then you could end up in a situation where the 3D printer isn't fine-grained enough, so you will actually have an extra layer that will fill in your hole or something like that. So a little bit of extra fuss factor. So for the post positions, we go through and we will translate to the position and then a little bit below the plate. And then we will create a cylinder with the plate thickness plus a little bit more with the diameter of the inner post. And then we have the latch slits here. I'm not sure if it's called a latch, but yeah. So the slits here, we will have a plate length, so in the middle of the plate, and then in the middle of the slit. So we will get them in the middle of the plate here, and then we will use the position from the edge and the middle of the width of them in order to say where they should be located. And then later down here we print out this translation here where we go to a particular place and then print a cube. And the reason why you don't have this is because the translate and the cube statements are on the same line pretty much. So you translate and print a cube in one action. So if we do like this, then you will have a translate that will not take effect on the cube. So translating cube should not have a semicolon in between. And then we have a slit length, slit width, plate thickness, and so on. I can make it a little bit larger so it's easier to read here. So that was what we did with the base plate. And then we print the base plate, and then we go through for all the post positions. We will create the screw posts at their particular position. And this is the same thing here. We translate to a particular place. And then we have this that is on the same line. So everything that happens inside of here is on this translate, and here we have a difference. So we create first a cylinder that has the post height and the outer dimension, and then we will translate to Origo again, and then we will create another cylinder that will create the inner dimension, and all the way up to the thread base thickness, so the thickness of what actually screws will be screwed into. So the post height minus that, and then we will do the same with the where we actually screw the screw hole. So that's the screw hole dimension, and then from the post height minus a little bit, and the thread minus the thread base thickness, and then we will do that for the thread base thickness plus a little bit. So that will create the actual thing that we can screw into. So that was our first model. The second model is much simpler. It's just this kind of larger compartment where we could put a hard drive. So this is the tray, as I call it. A hard drive is actually 147 millimeters in length. So I used a little bit more so I could put the cable in there as well. And then we had the wall thickness times 2, so we actually get some extra space there because we have 2 walls that we need to add as well. And then we do the tray width, which is the width of a hard drive, 115. So that was cool that the actual plate here that we screw into the over part here is similar thickness as a hard drive. That is a super strange coincidence. And then we will put the actual tray width and tray height here. You could figure those out, and then we will use the slit information in order to create these kind of latches, or what we call those. And then we have the cavity, what we actually will take out, and then we will figure that one out. So we will create the first cube here of the tray, and then we will create the inner cavity. So we translate the wall thickness in all directions, and then we will create a cavity here. And the latch, as I called it, we will translate to a particular place, and the tray height, so we will start off at the top, and then we will create a cube at the top here. That is the first little cube here, so that is the slit length divided by 2, and then we will do the same with the full slit length, but a little bit further up, so we will actually get the upper part here, so it's a little bit longer. And then we will create 2 latches, one on each side of this one. So not that complicated of code. It took me a while to figure all the different things out, but it's so nice where you can create these kind of module, I would say, functions, where you describe something and then you can reuse that multiple times in order to create this mostly readable code to figure out how to create a 3D model. So this was what I wanted to cover today. I hope you found this interesting. I hope that you liked this video. Give it a like, share it with your friends and colleagues. If you want to support the channel, there are links in the video description. If you haven't subscribed yet, please do that. If you have any comments or suggestions, leave those in the comment section down below. And I really hope to see you in the next video.